So in this video we're going to talk about equilibria. So what actually is a dynamic equilibrium and what is the symbol Kc? So a dynamic equilibrium is where you have a reaction that is simultaneously going forwards as the reaction is also going backwards. And it appears that the reaction has stopped and you have a constant amount of products at the same time as a constant amount of reactants that hasn't reacted. But this isn't true. You haven't got a constant amount because, like I said, the reaction is going forwards at the same time as going backwards, but at the same rate, so it appears frozen in time. So that's a dynamic equilibrium. But what is Kc? So Kc is actually the value that we can give to the position of an equilibrium. So if it's in the centre, the value of Kc will be 1. If it's towards the reactant, the value of Kc will be less than 1, and if it's towards the products, the value of Kc will be bigger than 1. And again, Kc just shows the position of the equilibrium with regards to the centre. But there is one principle that you have to know when doing equilibria. If a dynamic equilibrium is disturbed by changing the conditions, the position of the equilibrium moves to counteract the change. So basically, an equilibrium always wants to maintain a constant concentration, constant temperature, constant pressure, things like that. So it will move to counteract any change. So if we start with the first thing that can change the position of an equilibrium, and that's concentration. So here we have a simple reaction, not denoting any chemical in particular. X plus Y reacts to form A plus B, but it's in equilibrium. So it can react to form A and B, but A and B can also react with each other to form X and Y again. So what happens is we'll have at equilibrium, so we'll add X and Y, it will react together to form A and B. At equilibrium we'll have, say, this amount of the reactants and this amount of the products. So these are the concentrations. So what happens if we suddenly increase, say, the concentration of X and Y, if we increase this up to here? So now it's no longer in equilibrium. What will actually happen is this will lower the amount of the reactants and increase the amount of products to a point where they're then equal again. So about there. So we're now suddenly gained concentration of product but lost concentration of reactant to create this equilibrium that we see above. So it's tried to minimize that change by decreasing the reactants and increasing the products. Why is this useful? Well, it's useful because some of the products and reactions, take A and B here, could be really valuable, really expensive. A company could sell it for millions and millions per ton, whereas X and Y could be really cheap materials that they can buy in for pennies. And if you can just throw in more of this material X and Y that's really cheap to produce more of A and B, that's just perfect because they can increase profits. So if you increase the concentration of the reactant, if you increase the concentration of the reactants, it will react to form more A and B to minimize the change, shifting the equilibrium to the right. And again, this is very good for companies. So if we decrease the concentration of Y, then the equilibrium will just do the opposite. The equilibrium will just shift to the left because we now don't have enough Y for the system to be maintained. So A and B will react to produce more X and Y to get it back to what it wants to be, the original concentrations. So the equilibrium shifts to the left. Now, the next thing that can change the position of an equilibrium is temperature. So we've got here the X plus Y goes to A and B situation again, but if you remember from my enthalpy videos, delta H stands for the enthalpy of the reaction, and here if it's positive it means it's endothermic. So what this is saying is X plus Y going to A plus B, the forward reaction, is endothermic, so it takes in energy in the form of heat. Because of this, it means the A plus B going to X plus Y, the reverse reaction, means it's the minus of that value. So it's minus 150 kilojoules per mole. So that means the reverse reaction is exothermic. It gives out energy in terms of heat. So if you remember again, the position of the equilibrium will move so that the temperature becomes the same as it was initially. This means if we raise the temperature by, say, 100 Kelvin, the reaction wants to lower, the system wants to lower the temperature by 100 Kelvin to get it back to what it originally was. And to do that, it needs to absorb energy. So how does this system absorb energy? Well, we worked out that the forward reaction's endothermic, which means it takes in energy. So all it can do is just react more of the X and Y together to form A and B, and that absorbs the energy, lowering it back down to the level that it wants to be at. So in this case, when the forward reaction is endothermic, the equilibrium shifts to the right as the temperature increases. Okay, now what happens if we decrease the temperature by 100 Kelvin? Well, this means the system wants to be raised in temperature by 100 Kelvin because we just decreased it by 100 Kelvin to get it to its initial state. And to do that, it needs to produce heat energy. And to produce heat energy, you have to do the reverse reaction, because the reverse is exothermic, so it means it gives out heat by minus 150 kilojoules per mole. And because of that, that means more A and B will react together to produce X and Y. And that shifts the equilibrium left, because more X and Y is produced, so the equilibrium lies to the left. And it's as simple as that. You just have to look at the delta H values. So if it was the other way around, the forward reaction was exothermic and the reverse reaction was endothermic, then we would have the reverse situation where increasing the temperature means the equilibrium shifts the opposite way to the one I've just discussed. So you just have to look at the symbol in front of the number, if it's a plus or a minus. That's very important. Okay, so that's temperature done. If we look at something else, which are catalysts, as you may know, a catalyst basically speeds up the reaction, and you may think this interferes with the equilibrium. Actually, it does not. Catalysts do not change the equilibrium position. It only allows the equilibrium to be reached quicker. And the reason for that is you have a reaction, so you have reactants going to products. That gets quicker, let's say 10 times quicker. But in an equilibrium, you also have products going to reactants. And because it's a catalyst, that reaction also gets 10 times quicker. So you have reactants going to products 10 times quicker, and products going to reactants 10 times quicker. So it just reaches equilibrium quicker, but the equilibrium point's exactly the same. So let's say it was dead center, it'd be dead center again. It just reaches it quicker. It doesn't change the equilibrium at all, and I need to stress that. Okay, so the final thing on this video that we'll talk about before I do some examples is pressure. So pressure can change the position of the equilibrium again, because the position of the equilibrium will move so that the pressure returns to its initial pressure. So if we have an example here, everything's in the gaseous state, as you can see. So this is our x plus y goes to A and B, except for we've got different numbers of x and y going to different numbers in A and B in this example. And this is the important bit. So here you can see, if you add them together, we've got a total of 7 moles of gas. So you've got 5 of x and 2 of y, makes 7. Here we have 5 moles of gas. Now, pressure is defined as sort of the amount of molecules hitting the surface of your container per second or per time. And because of this, we've got 7 moles of gas on the left, 5 moles of gas on the right, so we have a total of like 13 moles of gas hitting the container, creating a random pressure. Now, if we increase the pressure, so pressure's been increased, suddenly we don't have the same pressure before, and the system wants to move it back to the pressure that it was. So how it does this is by producing less moles of gas. So the equilibrium actually shifts right in this case, because we've got 7 moles of gas goes to 5 moles of gas. To decrease the pressure, we need to have less molecules hitting the surface of your container. So if we can reduce the amount of molecules, so 7 to 5, we'll do that. So we'll shift the equilibrium right, having more of A and B and less of X and Y, and that will cause the pressure to be decreased to its initial state. Okay, so what happens if we decrease the pressure? Well, you can probably realise that there's a trend going on here with all the other examples. It's just the reverse. So to decrease the pressure, if the pressure is decreased, we need to increase it to get it back to its initial state. So how we do that is by producing more gas. How do we produce more moles of gas? That's react the less to create the more. So react the A and B to create X and Y. And that shifts the equilibrium to the left because we now have more X and Y. So the equilibrium lies to the left. It's as simple as that. So when pressure increases, the side of the equilibrium that has more moles of gas will decrease and it will shift to the less moles of gas. If we decrease the pressure, the side with less moles of gas will react to form more of the higher moles of gas, shifting the equilibrium to the left in this case. Okay, so now if we go on to Kc, now Kc is actually a value. 1 is the centre, so the equilibrium relies exactly 50% of products and 50% of reactants. But if it's less than 1, that means it lies to the left, and if it's greater than 1, it means it lies to the right. But how do we actually work out Kc? So if we have a simple reaction, X moles of X plus Y moles of Y is in equilibrium with A moles of A and B moles of B, then we can actually work out the Kc of that. So Kc is defined as the concentration of the products, which the square brackets is a shorthand for concentration rather than writing concentration. So it's the concentration of products over the concentrations of reactants. So in this case, what's the concentration of the products and what's the concentrations of reactants? So the products are A and B. So we have the concentration of A to the power of little a, the number of moles you have, times by the concentration of B to the power of little b, the number of moles of B you have, over the reactants, which are X, concentration, and the concentration of Y to the power of Y. Now the reason why you have these powers of A, B, X and Y here is because if you have 2 moles of X, that means you've got like a X and X reacting. And if, as you can see here, everything's times by each other. So X times by X is just the same as X squared. So you can just have the number of moles as the power. So if you had 3 lots of X, it would just be X times X times X, which is X cubed. And that's where you get your powers from, and that's why you have those powers there. So now we have the formula for Kc. We now then need to look at units, because if we know the concentrations of all these and how many moles there are, we can work out Kc. But Kc's units will always vary depending on what you have. So if you remember Kc's products over reactants, the concentration is moles per dm cubed. So if we say we had the concentration of products to the power of 3, so we had A times by B squared, so to the power of 3, over the concentration of reactants to the power of 2, so we had 1 lot of X and 1 lot of Y, then that's the same as saying moles per dm cubed as this concentration cubed over moles per dm cubed squared. Now, anyone who's done GCSE maths knows if you had 2x over x, you can cancel out those x's just to leave 2. Now here, what we can do, because we have moles per dm cubed over moles per dm cubed, we can cancel them out. Because it's squared, we lose 2 of them, and we lose 2 of them, just to leave moles per dm cubed. Therefore, the units in this case is moles per dm cubed. And you'll see in later examples, we actually work out the units for some examples. So, example 1, if we do it algebraically, just to show you the general way of doing it, and then we'll actually look at some number ones later on, and a complicated example you'll have to do at some point if you want higher grades. So if we want to work out Kc, it's concentration of products over the concentration of reactants. So the products are A, so the concentration of A, and because there's only one molecule, it's to the power of 1, so we can just ignore the power, times by the concentration of B, as we have 5 molecules, is to the power of 5, all over concentration of X, and as we have 5 molecules, it's to the power of 5 again, times by concentration of Y, and as we have 2 molecules, to the power of 2. Now that's what Kc would be, algebraically. If we had the numbers, we would put the numbers in for X. Let's say it was 1 mole per dm cubed, we'd just have 1, say B was 1, we'd have 1 times 1 to the 5, and so on. You just put the numbers in, and you have a number at the end once you put it in your calculator. But now we want to do the units. So, the units here, again, are mole per dm cubed, and my pen's gone weird again, moles per dm cubed, but we have 5 and 6, so it's to the power of 6 over moles per dm cubed again. However, we have 5 and 2, so we now have it to the power of 7. So what this means is we lose all these because we've got 6, and we lose 6 of them to leave a 1 there, which is anything to the power of 1 is just itself. So that means it's 1 over moles per dm cubed, which is same as moles to the power of minus 1 dm cubed. And the reason why is moles to the minus 1 dm cubed, 1 over x, if you've ever done maths, is the same as x to the power of minus 1. So when you have anything to the power, it just means 1 over. So here we had mole is equivalent of moles to the 1, so we just put a minus in front to flip it over, so we don't have to do a 1 over. And here we have a minus 3, so we just change the sign to a 3. And that's how you get those units. Okay, so let's look at example 2. Here we have a reaction of I2 plus H2 is in equilibrium with 2HI. So a mixture of hydrogen and iodine was heated in a sealed flask. The concentration of iodine and hydrogen was found to be 2.5 times 10 to the minus 2 moles per dm cubed, and the concentration of hydrogen iodide was 1.71 times 10 to the minus 1 moles per dm cubed. Calculate Kc. So we know that Kc is products over reactants. So products, in this case, are HI, and because we have 2 moles of that, it's squared, over the concentration of I2 times by the concentration of H2. And there's only 1 mole of each, so it's just itself because it's to the power of 1. So when we put values in there, we have 1.71 times 10 to the minus 1 squared, as it just says that value here, over 2.5 times 10 to the minus 2 times by 2.5 times 10 to the minus 2, and that value is stated here in the question. So when you put that in your calculator, you'll get a value of 46.8. Okay, we have a value, but now what about the units? So it's a concentration over concentration. So concentration squared, so we have a concentration squared over a concentration times a concentration, which is just a concentration squared, as they've got the same units. So they cancel out with each other, leaving no units. Therefore, the answer is 46.8 with no units. That's the answer to this question. So, example 3. Now this is a bit more complicated because they give you Kc and the initial concentrations, but we want to know the concentrations at the equilibrium. Now this requires a bit more maths. If you think you know how to do it or would like to have a go, pause the video and restart it in a few seconds time and we will talk about how to do it. Okay, so if you had a go, this is how we'll do it. So the question is, CoCl2 is in equilibrium with CO and Cl2. Given the equation above, calculate the equilibrium concentrations of each molecule when Kc equals 0.680. The initial, denoted by this little zero here, means initial concentration of CO is 0.500 and initial concentration of Cl2 is 1.00 moles. So initial here for CoCl2 is 0, as it stated the initial concentrations. CO is 0.500, Cl2 is 1.00, and here we have to look at significant figures, as we've got 3 significant figures. So we're looking at the change. So because CoCl2 increases as CO and Cl2 are going to react, that means we're going to have a change. It can only go up, it can't physically go down. So we have a change of x. Here we have 0.5 to begin with, but it's going to react to lose x because it's a one-to-one relationship. So it's 0.5 minus x, as it would have lost that much to react. If, for example, we had a 2 in front of the CO, it would be half that, as 2 moles are going to make 1, so it would be half of it's being made, so you would lose double the amount, you would lose 2x. In Cl2, we have 1.00 minus x as well, because again, it's a one-to-one reaction, so it loses x. So how do we work out what each one is at equilibrium? Well, this is when maths is involved. So what we can do, just to the left here, is set everything up. So what we have is Kc, it's the concentration of products, CO times by Cl2, all to the power of 1, over CO Cl2. Now what that means is, because we're given Kc and Cl2 and CO, oh, that's at initial, sorry, to work it out then, we're given Kc as 0.680, and we can substitute what we did as the change. So the value for CO at equilibrium will be 0.5 minus x, and the value of Cl2 at equilibrium is 1 minus x. So we've just written it out here. And the value of CoCl2 is going to be x. So what we can do then is set up a simultaneous equation, or a quadratic I should say. So 0.680x, all I've done is just brought the x up, times it by x, and I'm going to expand the brackets out at the top. So that gives x squared minus 1.5 x plus 0.5. Now I'm going to go on to a new slide just to continue the rest, as we don't have enough room. So all I'm going to do is write that bit down again, what we just got. So 0.680x equals x squared minus 1.5x plus 0.5. Just rearrange that to 0 equals x squared minus 2.18 x plus 0.5. All I've done is just brought the x over there, so I've minus 0.680x on both sides to leave 0 equals that function. So how do we get x of a quadratic? Well, we can't simply put it in brackets because they're not nice numbers to work with. So what we'd do is use the quadratic equation. So that is defined as x equals minus b plus or minus the square root of b squared minus 4ac all over the power of 2a, where a is defined as the term in front of the x squared, b is defined as the term in front of the x, in this case minus 2.18, and c is defined as the term at the end here, which is 0.5. So we can put that in. So x equals minus b, so minus 2.18, so it's 2.18, plus or minus, so we'll have two different things here, of b squared, so minus 2.18 squared, minus 4 times by 1, a is 1, times by c, which is 0.5, all over 2a, which a is 1, so it's all over 2 times 1. And when we put this in the calculator, we get x equals 0.260 or 1.92, because we've got this plus or minus symbol, so you put in plus, you get one value, you put in the minus symbol, you get another. Because we know the original concentration of Cl2 was 1, and the original concentration of CO was 0.5, and the value at equilibrium is 0.5 minus x, or 1 minus x, depending which reaction, which product you're looking at, you can't have 0.5 minus 1.92, because if not, you'd have negative chemicals. You can't have negative chemicals. That's not how the physics works. So therefore, x cannot be 1.92. So let's get up another slide. So if x can't be 1.92, that means x has to equal 0.260. Brilliant, we found out x. So now what we can do is work out the concentrations of each. So the concentration of Cl2 was x, so therefore it's 0.260 moles per dm cubed. The concentration of CO and the concentration of, concentration of CO equals 0.5 minus x, which now when we've got 0.5 and we minus x, that gives us 0.240 moles per dm cubed, which is the same as doing big M, molar. And the concentration of Cl2 is 1 minus x, which equals 0.740 molar. And if you remember, I was talking about significant figures earlier. Cl2 was 1.00 molar, and CO was 0.500 molar in the initial concentrations. Got 3 significant figures on this one and 3 significant figures on this one. Therefore, give the significant figures to 3 in the answer. So there you go. There's your answers to that. Now this type of question is one of the more complex questions that you'll have at A level to do with equilibria. But if you can crack that, especially if you're mathematically minded, it shouldn't be too difficult for you after a couple of practice attempts. You'll be able to do this and pick up a lot of marks in exams. So I hope this video has helped. Please like, share and subscribe for more videos. Let me know if there's any topics you want me to cover that I haven't done anymore. Just write in the comments below or send me a message and I'll do them as soon as I can. Thank you.